All right, so let's continue our presentation regarding this virtual keyword and what kind of change does it make in the internal organization of our objects in memory. So basically, without virtualization, without virtual, our object such as this customer looks like this in memory, right? It has two parts, and I don't know their sizes, but this is the phone, right? And this is the address, and this is what the object looks like, this customer thing. Okay, so this pretty simple arrangement. Now notice that, of course, when the executable program, our executable image, right, some kind of executable image, the final product already compiled and linked, is loaded into memory, its memory segments are organized in such way that there is a text segment, right, text right here. The text will contain all of our code. So all constructors, all print functions, and all other operations that we add to our structures and classes, all of this, right, all of this, and all of this, all of it is going to reside in the text segment. The code stored in the text segment like this. The object on the other side are actually residing in the data segments, constant data segment or global data segment or stack data segment, depending where the object is created. So this is the data, global data or stack data, and it's separate from the code. Okay, so then when we make this change and we add this virtual keyword right here, once function is declared in the base class virtual, it continues to be virtual in derived classes, right? So the virtuality of the functions are or is inherited in derived classes, and that's the idea of the virtual keyword. You can actually add it here as well if you want to, but it's not necessarily a good practice, because it's nice to keep it as clean as possible, and once declared virtual, it's a virtual function. So now when we once again, just let's go back to our data and code segment. Okay, so we have image of our executable program loaded into memory like this, and it has the code segment that contains all the code, this code, all functions, and data. And let's say that we create this object right here. Right, so we create our first customer object. So the object is created right here, somewhere in the data segment. And of course it will have the phone, the address, but virtual adds, like we already saw in differences when we started measuring sizes of the customer, it gets a hidden data member, which is a pointer to a virtual table of virtual functions, VTBL. Compiler generates VTBL like this, and so it has entries in the table, and this is the pointer to a VTBL like this. I'm not going to finish it just yet, but we have 1, 2, right, and the third version, first, second, and third versions of print. Of course, in the text segment right here, somewhere there will be these functions placed in the text segment, already compiled with executable instructions. And this virtual table, VTBL, let's name it this way, virtual table, will have addresses of the functions as they correspond to different types of objects, like this. Okay, so this, say, will be for the customer, this thing will be for the company, right, and this will be for the person, P. Okay, so these are different functions, and these three functions are here in our memory. And the table here contains the addresses, physical addresses of these functions in memory. So now when we create the customer, okay, so now we just say first line here, create customer, right? So we construct the object. So it will have this hidden data member, and then of course it will contain the phone, and it will contain the address, which is a string, and this will be our object, and you see that now there is a hidden data member. So where is part of virtual table responsible for storing addresses of functions which correspond to the customer structure? Right here. So this pointer is going to be pointing to this portion of the virtual table. And if at runtime we stored address of the customer right here in this vector of pointers to all sorts of structures that we defined, then what's going to happen if we say print, and if this was just the customer like this, compiler generates code at runtime right here, okay, so that it goes, picks up this pointer, dereferences this pointer, and says where is the entry for the print function, and the table contains the entry, and the table will direct the runtime call to this version for the customer, right? So this is like this is the version for the customer right here, and this is the version for the company, and this is the version of print for the person. Okay, so the next time we instantiate a company, instance of a company, the second case, all right, in that case, its copy in memory will have this extra member, right, which is pointer to the virtual table, but this time the pointer will be into the part of the table that corresponds to the type of a company, right? So each class that participates in this hierarchy and uses virtual functions has part of the virtual table dedicated to its own. All right, so virtual table does not belong to objects. It's just static table of statically already compiled functions, all of these versions. And like I said, if we're trying to print, and this is the pointer to the company, this hidden address contains the address of the part of the table that happens to correspond to the company structure. And there is an entry, like an address of the function right here, right, which is a print function for the company. And therefore, this is how it works. Basically, it's like one hop and the second hop, and now the function executes. So this is how it actually is implemented, right? Because we have a hidden data member right here inside our object, which uses virtual functions, okay, just one, the size of your pointer type on x86 is 32-bit, on x64 here on my Windows Intel platform, it will be 8-byte size long object, and we already observed when we measured the sizes that it all fits together, right? And so this hidden member, hidden pointer increases the size of our object by this many bytes, right? So this is what you pay for, well, you know, or what you pay for adding virtual functions. However, there will be only one. So if I have many virtual functions in implementation of my customer, not just one, but multiple, all sorts of virtual functions, if I'd like to have, it only stores one of these pointers. It doesn't store multiple pointers, because this pointer is just like this table will have more entries. The table will have entry for each function, and this entry will have an address of the corresponding function, right? So we have these functions, whether they virtual or non-virtual, they're all placed inside the text memory segment, and this is where the functions are. Okay, and but then when we create objects, the objects themselves have a pointer to the table that has addresses of virtual functions. Now, once again, if this virtual keyword is not present here, so it's gone, none of it, everything goes back to extremely simple thing, where it's just like our object does not have any hidden data members. It only will have the phone entry and the address, and none of these crazy mechanisms, you know, delegating or dispatching the calls are happening anymore. It's just like for this object, this function will be invoked. For this type of object, this function will be invoked. There's nothing virtual, nothing you know, behind the scenes, any kind of behavior. Okay, but as soon as we add it back, the virtual keyword, right? So it starts using this mechanism to dispatch calls to corresponding functions at runtime. So this manipulation of the hidden address of virtual table, which then directs the call to the appropriate function, is happening at runtime. So it takes a little bit of slowness, but it's very negligible. It's just, you know, just a couple of CPU cycles wasted on this, but the benefit for most application is enormous, because now you can utilize this. On this line, we have the example of our polymorphic behavior that was presented, or as we start presenting in our slides.